In this video, we're going to continue our conversation about controls and begin to discuss a process for designing a controller that makes your system behave in the way that you want it to. Um, so the process that we're going to be looking at is a has 4 steps. So we're going to have 4 steps to control design. Um, the first step is to determine the nominal control input required. So determine nominal control to keep the system at the desired state. So the question we're asking ourselves here is, in a perfect world, if our model is perfectly accurate and if there are no external disturbances, what is the force that I need to do what I want to do? And that's usually and you can usually determine that just with math, right? So for example, we talked about the car. I'll draw a little car here. Going at some if you're doing cruise control and you know that um, and your desired velocity is 70 miles per hour. The engineers who built this car probably have a pretty good model of how fast the car is going to go based on the gas pedal, the input to the gas pedal, given some particular circumstances, right? So if maybe the air pressure is at sea level and there's no wind, so we've got just basic air resistance on flat ground on a new, well-kept road, um, then they're gonna know how much the gas pedal needs to be put down under those perfect circumstances to get that nominal 70 miles per hour. Um, Same thing uh, with maybe a pendulum, right? If you have a pendulum, you've got some mass m and some length L, then if you want this pendulum to go out to 90 degrees, um, and you're able to apply some torque to it, based on the mass and the length and gravity, you know that that torque is going to need to be something like mg L sine of pi over 2, which is 1. Um, so, and so that's going to be the nominal control input. And in a perfect world where the mass is exactly what we need it to be, the model's perfect, and um, there's no disturbances, then you'll get a perfect output, and it will go exactly to 90 degrees. But unfortunately, the world is not perfect, and um, we need more steps. We need 3 more steps. Um, so step 2 is to rewrite your ODE or rewrite your model in terms of the error between um, between a nominal value and the actual value. And it's this error that's going to give us more information about the force that we need to apply, or the voltage that we need to apply, or the input that we need to apply to get to our nominal value. So our error which we usually write as x tilde or y tilde, is going to be equal to x minus x nominal, where just the regular x is your actual position or actual state, and x nominal is your desired state. And when we plug these things in, when we're going to plug this equation into our equation of motion, we usually take x, we usually rearrange it so that x tilde plus x nominal is equal to x. We'll show an example in a later video. The third step is to draw a block diagram to visualize the mathematics. And a block diagram is a tool that we use, like it says, to visualize mathematics, particularly when we start to use the error, the difference between some desired value and some actual output. So typically with a block diagram, you'll have something like x nominal going in, and um, if we were just going to do our nominal control, for example, then our x nominal would go into a block that says nominal control. And this block is a function that takes in some value x nominal and spits out some force nominal. Remember, we're trying to pick a force to make a system do what we want. So if we know some x nominal, we do the math, like on the pendulum above, and we get a force. And that force goes into what we call the plant. And the plant is the actual thing that you're controlling. It could be the car, it could be the pendulum. It's the thing that's being modeled. And we call it a plant because control systems were actually invented by chemical engineers who were trying to make their chemical plants act the way they wanted them to. So that's the word that we use. And so if you give your pendulum a force, for example, you're going to get out some x actual. Um, and that's based on the force that you're applying to it. So this is a block diagram for what's called open loop control. It's an open loop block diagram. If we wanted to, on the other hand, have a closed loop, that's when we start to take the error into account to get better control. So I'm going to go ahead, I'm just going to erase this so I can edit my block diagram. So this is an open loop. We have an input and we have an output. So we take this output and we take this signal or the value of x back and we combine it with x nominal in what's called a summing junction. So if we have a circle, that usually means the two values are being summed. And because x tilde is equal to x minus x nominal, I'll just put a minus here and a plus here. So that means that we take the value of x from the bottom, positive, and we take the value of x nominal from the top, and it's negative. And we take this value, and what comes out of that is x tilde, or our error. And then we define some error control law. We do some math on this error to come up with F tilde or some other force that we're going to add to F nominal. So I'll bring this up here, and what I'm going to do is I'm going to change what's coming out here. I'm not going to change it. So we still have F nominal coming out of nominal control, but we'll go ahead and add those two forces together. So F nominal plus F tilde is the total force that goes into the plant. I'll call this F total. And so this becomes a closed loop system because the input, or the output, sorry, is connected back through this loop, through this signal, back to the nominal. And when we're choosing our force, we have information about what the system is actually doing. And this is how we're able to get disturbance rejection. And so I'll cover step 4 and do an example in the next video.